Hi everyone, I am Balaji, and in this video I will be talking about my work aggregation algorithms in Federated Learning, which I did while interning at KLIV lab at IIT Kharagpur under the guidance of a PhD student named Anubham Botako. So I will just give you a short intro about Federated Learning for people who don't know. So Federated Learning is one of the privacy preserving machine learning techniques, so which is used to protect the user's privacy. So in the case of Federated Learning, we have a single server and multiple clients. So each client has its own data set, so which might have a different data distribution than the data sets that we get from other clients. So the server has a global model or a model, so which needs to be trained on the data which is distributed across multiple clients. So the server will send its global model to the participating clients. So each client will receive that global model and train that model on its own data and sends back the trained model to the server or an update to the server for the model. So then the server aggregates all the received models from clients to form a new global model, which will again send to the clients for further training. So this process repeats for certain number of communication rounds. So so at last, we have a test set on our server after running our Federated Learning setup for about some communication rounds. We will test it on our test data set, which is located at our server side. So Federated Learning, in short, like we are not optimizing a single function or single loss. So instead, we are optimizing a sum of losses. So from each client. So we care about the performance of our global model on multiple clients, not just a single client. So the problem is easy to solve in that case. So which is usually a centralized training setup, which we might came across in machine learning. So, what's the difference between federated learning and traditional machine learning? So, in the traditional machine learning setup, the data that we need, which is needed to train our model, is situated on our server or a data center itself. So, there is no need for sending our models to other servers. So, we perform. So, this is also called a centralized training. So, the data set is also generated by a single data distribution. So, yeah, in case of Federated Learning, the data is distributed across multiple clients. So we don't have the option to collect all those data since we are caring about the privacy of that data. So we can't able to centralize it on our server due to privacy concerns. So then we perform distributed training. So the data in across the clients aren't generated by a single data distribution. Okay, each client has its own data generating process. So in my work I have implemented these five algorithms: fed average, fed averagem, scaffold, fedopt. So in the case of fedopt, there are three kinds of algorithms that I have implemented: fed data guide, fed adam, and fed ahoy. I will talk about it later. And mimelight. So there are a few subtleties that I need to talk about before talking about my work. So regarding client communication first, so in the case of Fed average and Mimelight algorithms, so the client communicates the whole trained model, the state dictionary of the trained model to the server. So, but in case of other algorithms, scaffold or FedOpt, the the client or fed averagem, the client communicates the difference between trained model and the model that it received for training. Okay, so this difference can also be stated as an update for the trained model. Okay, yeah. And regarding control variant, so some algorithms like scaffold or mimelight or mime also makes use of something called control variates. So in that case, the server needs not only to send the global model to get trained on the client's devices, but the server now needs to send two two things: one is global model and one is control variate. So and the client also needs to send back the update for the global model and the control variate also. So In the case of Mimelight, the optimizer state. So the Mimelight uses optimizer state, so which can also be thought of as a control variate, which needs to be sent to the clients. So regarding initialization of control variate and optimizer state. So the control variates and optimizer states can be initialized with the zeros. So matching the shape of the model that we are optimizing. So yeah. And so, and the notation that you can see, X is the global model, YI is the local model that is being get trained on the client I, and G is the gradient or average of the model difference. So from participating clients. So here the model difference is an update or which is calculated between the trained model and the received model on client side. So S is the optimizer state, eta G is global step size or learning rate on the server side, and eta L is the local step size or learning rate on the client side, and T represents the communication round that we are in. So first, let's just talk about an algorithm which started off this field. It was introduced by McMahon from a Google group. So in this paper only they have introduced a communication efficient learning of deep networks from decentralized data. You can also read the blog. So this is one of the widely recognized and accepted algorithms for doing Federated learning. So whatever Federated learning algorithm that you might come across in future, it will cite this work. So since it's the beginning point of everything, like AlexNet in the case of deep learning. So this is the original pseudocode which I taken from the original paper. So you can, I will. So each client trains the received model on its local data using SGDs, just a simple stochastic gradient descent, and the client will send back the trained model to the server. So then the server receives all the trained models from all the clients, and the server averages all the models and initializes it as a new global model. So this global model will again sent to the clients for further training. So this process repeats for a certain number of communication rounds, as you know. So in the case of client, so the X, which is the model that we received from the server, it gets initialized at yi. Then we are gonna update this yi, which is our local model, using a stochastic gradient descent. Like as you know, the this is eta, and which is a learning rate, and the gradient is the loss with respect to yi's parameters. So after the client performing the SGD, then it will communicate the updated model, the trained model, to the server. So all clients will do that. This is just a client I. So all the clients participating in each communication round will communicate this OI trained model to the server. So what the server does is it just averages all these YIs and set it as a new X. So and it will again communicate this X to all the participating clients. So if you look at the equation, we are just summing all the yi's and we are dividing by s. So here the s means the number of clients in each participating round. So it's just an average. So that's the name Fed average. So let's just talk about Fed average M. So Fed average M is nothing but Fed average with server momentum. So you might have come across adaptive optimizers, momentum, Fed, Adagrade, Adam, RMS prop. These are kind of algorithms which adapts its learning rate based on the based on the optimizer state. Okay, so in the case of Fed average M, they make use of a modified version of momentum method, so called a Nesterov momentum. So I have implemented this only. So the update rule for the server is similar to the SGD update rule. So here we have like this kind of averaging at our server side, but in the case of fed averages ems. So the update rule for the server is similar to SGD update rule. So here you can read the paper. So momentum method. So in the momentum method, we maintain a state called a velocity, which accumulates the past gradients. So during optimization, first we update the v using the gradient that we got from back propagation. Then we use the v to update the model's parameters, like in the case of simple SGD. So here it is learning rate. So what's the difference between is, so instead of updating using G, we are just updating using V. Okay, so here V is from the previous time step. In the case of the first round, this will be initialized at 0, so it has no impact on the first round. Okay, so beta is called a momentum, which is a hyperparameter. Usually it is set to 0.9. So it means the 0.9 percentage of the previous states v is taken into account for computing this new velocity. Okay, so and the full gradient is calculator is used for calculating this v. Okay, and Nesterov momentum or Nesterov accelerated gradient. So this is similar to momentum method. So after updating v using g, then we again update the g using v. Okay, so if you look at the equation, so this is similar to previous one. Here we are again just adding the beta of v to our gradient itself. Then we are just updating the model using our newly computed gradient here. Okay, so Nesterov momentum is based on the formula from on the importance of initialization and momentum in deep learning from Jeffrey Hinton and Ilya Sutskever. So this is the pseudocode for Fed average m. So in the case of a client, so x will be initialized as yi, then yi will be updated. So then we are again computing delta yi, which is a difference between the yi, which is our trained model, and the model received from the server. So this is called updates or model difference, which needs to be communicated to the server at this point. So then the server just averages all these delta y's, and as you can see, that it first in v is initialized as zeros in the case of first round. Then we will update the velocity using our gradient. Then since Fed average m implements Nesterov accelerator gradient, so g will also gets updated. So x is equal to x plus eta g. So in the so we don't so indicate when we are using the model differences like this, we need to add a positive, not negative. So if you if you do use negative in spite of positive, then your model won't work like after 3 or 4 communication rounds. Okay, scaffold. In the case of scaffold, so this is the first paper to propose the idea of control variates to correct for the client drift in its local updates. Okay, so two control variates are used in the case of scaffold, one for server and one another for client. So this is the pseudocode. So here in the case of client I, so the y is initialized from x, and the c, this is the control variable from the server, which is also sent by the server. Then we are going to update yi, not just using the gradient that we calculated, by minus ci plus c. So here minus ci is client i's control variable. So it maintains the state of ci. So next we are going to compute ci plus. So we can able to calculate it using two methods, but I used the second method ci, since I need to compute the gradient with respect to x. So it is quite expensive, so I used the second method. So ci minus c plus k 1 divided by k eta l. So here k is the number of clients participating in the current epoch that the client is in. So okay, so then we have x minus yi. So yeah, so after that we will complete compute the model difference delta yi, then we will compute the delta ci. So after that we will update our client's control variable, which is ci, to set to ci plus. So then after performing this, the client will communicate delta yi and delta ci. So in the side of the server, g, which is nothing but the average of the model differences from all the clients, so it will be set as a g. Okay, then we have delta c, so it is just the average of delta ci's. Then we update the then we update our global model using this rule, and then again we will update our control variable at our server side using this rule. So here s is nothing but the number of clients participating in each round, and divided by n, which is the total number of clients that are available, and using delta c. Okay, and fed out. So in this paper, what they are describing is they proposed to make use of adaptive optimizers, which are very successful in deep learning, such as Adagrad, Adam, or it can also be other algorithms like RMS prop. So something like us, how we can use those adaptive optimizers in the case in the context of federated learning. So they included only these adaptive optimizers into server only. So we can't use this optimizer for clients, but we can use this for servers. Okay, since client cannot maintain states between communication routes in the cross-device federated learning setting. Okay, so this is the paper. So this is the gender framework. So you can use any kind of adaptive optimizer which stores average of the past gradients. Okay, and so I'll just discuss about three methods that I have implemented. So Adagrad and Adam, Yogi, to know about it better, you can check out this books chapter on optimization, dive into deep learning books chapter on optimization. Okay, so here's the pseudocode from the same paper. So in the case of fed data grid, so we have a client. So this is just the same case in the case of fed average. So client I will compute the model differences and send to the server, and the server just averages it and set it as a gradient. Then S, which is the optimizer state, which at the first round will be initialized at zeros, as I have talked previously, and we just add the gradient square to the S, and after we will update the X using this rule here, eta G is the learning rate divided by square root of S plus epsilon. So epsilon is a 10, like very small value, so which is used to not get 0 on the denominator side, so that we can't able to get a infinity on the spot. So usually so I have set it to 10 power minus 6 so in my implementation. So and after that the server will communicate this updated new global model to the participating clients. So in the case of fed adam, so as you look at in the case of fed Dohi, so in all the three cases, the clients will perform these same updates, same algorithm. Okay, so but the server algorithm will be different. So here we just average computes a need gradient using these model differences from all the clients. Then we have a two optimizer state in the case of fed atom. One is M and one is V. M is also known as first moment vector and V is second moment vector. So we also have two hyperparameters. One is beta 1 and beta 2. So beta 1 is set to 0.9 and beta 2 is set to 0.999 in my implementation. So you can see how the step works. So then we compute an updated value for m, our optimizer state using m divided by 1 minus beta 1 of t. So here t is the communication round that we are in. Okay, so and after that the global model will be updated using this updated m hat and b hat. So here also we will be using epsilon to not get an infinitive value. So in the case of Fed Yohi, so there's just a one slight difference in how we are gonna compute the v. Okay, so there's just a slight difference between Fed Adam and Fed Yohi, which is in how we are gonna compute this second moment vector or v. So so what SGN means is, so it just takes sign signatures, positive or negative values from this tensor, okay, g square minus v. So let's talk about MIME-Lite. So MIME-Lite mitigates client drift by making use of control variables like scaffold, and MIME-Lite also makes use of server level optimizer state, like in the case of Fed averagem and Fed up. So in simple terms, MIME-Lite is nothing but scaffold plus Fed opt or Fed averagem. Okay. So here's the pseudocode. So in the case of MIME-Lite, so MIME-Lite, as you can see, it makes use of FedOpt. So in the case of FedOpt, we have several adaptive optimizers. In my implementation, I have used the momentum method. Okay, so we can also make use of any kind of optimizer, adaptive optimizer which has a state. Okay, so here the client will be initialized with X and SI. So S is the control variable, but in the case of MIME-Lite, it's just an optimizer state. Okay, then we will compute the gradient, which is this term, and yi is equal to this is the update rule for the local model. So here eta is the learning rate, mu is the how we are gonna. So this is the base optimizers. So how we are gonna compute a gradient using the gradient calculator and the optimizer state. So then we again calculate the gradient, but with respect to access parameters. Okay, this g of x will be communicated to the server, and yi the update and the train model also gets communicated to the server. So in the case of the server side, we the all the gradients. So the all the gradient with respect to x gets averaged, and it is stored at g, and the state get optimized using this gradient and the previous state. Okay, then we are just averaging x is equal to this term as in the case of Fed average. So in the case of, so if you are not gonna able to understand what this is doing, like you can able to understand in the next slide. So the only difference is I have written this update rule, okay, but using in terms of momentum method. So the momentum is nothing but 1 minus beta of gi and plus beta of si. So state and the gradient. So that's it in the case of momentum method. So in the case of server, it also has the update rule, which is 1 minus beta of g plus beta of s. I hope you are gonna able to understand all these equations. Okay, so you can see my work, my on the implementation of these algorithms at this repository, which is also open source. Okay, thanks for your attention. Bye.